this first one, if you got 60t plus c, you're thinking in terms of an indefinite integral, and that was what we started with the beginning of chapter 5. And that actually is going to come into play today, but what I want you to go back to is the fact that that definite integral, which we learned a couple of days ago, is equal to a sum of an infinite number of rectangles on a certain area. Does that make sense? So for right now, what I'd like you to do is consider 0 to 3, so 0, 1, 2, 3, of the horizontal function at y equals 60. So from 0 to 3, under the curve y equals 60, you're going to find that area. We should end up with 180 here. Okay. What'd you get for the second one? 8? You got 8. 8 is correct. If you got 12, I'm thinking, I think we might need to check our bounds. Because we want to go from, we want to go, the function is 2t, and we know that's a linear function with slope of 2, so I'll just approximate it there. Here's 0, here's 1, here's 2, here's 3, and we want to go from 1 to 3. Geometrically, that's a trapezoid. Yeah, if you went 0 to 3, you might have gotten too much. But if you go from 1 to 3, you've got a trapezoid where this base is 6, this base is 2, and the distance between the bases is 2, so it's 1/2 of 2 plus 6 times 2, and that ends up with 8. How about C? What'd you get? Did you come up with anything for C? 18, what did you use? You got 9. If those of you that got 18, what did you use? Did you draw a picture? What's that function look like? It's a parabola up 3, right? And I want to go from 0 to 3. So the area, that's actually not very good. Let's go that being 3. The area we want to find is this. What's the problem? It's what? It's a curve. So what options do we have at this point? Can we find the exact value? Just say no. Can we find the exact value? No. What are our options? This is review. We could use a trapezoid rule. How many trapezoids? We could make 1. What would be better than 1? I think 3 would be a pretty good number of trapezoids here. 1, 2, 3. You could do that. Okay, I'm not actually going to go through the work on that, but you could do that. All right, so the trapezoid idea, does that make sense? Regardless of whether or not we're going to do it, is that okay? What else could we use? You could use an LRAM, an RRAM, or an MRAM. But at this point, we don't have the tools to calculate that exact area. After today, you will. So today's lesson is based on the idea that I'm going to show you how to evaluate a definite integral without using geometry. And it's going to be easier than you think. Okay, so go ahead and go to that second page in your notes. Okay, so this is what we talked about last week. We talked about the fact that a Riemann sum, areas of rectangles, as I let the number of rectangles approach infinity, is defined as a definite integral. And I still want you to understand a definite integral from a geometric sense, because in some ways geometry is going to be easier. If the function is nice, geometry is easier than what we're about to do. Okay? So, here's the fundamental theorem. Let's kind of jump into this, and I'll try to give a little bit of reasoning for it. But the fundamental theorem of calculus, if you go ahead and take a look at it, the key here is that a definite integral is defined as an antiderivative evaluated on the bounds of integration. So, a couple of key things. Capital F of x can be any antiderivative of the original function. So this will work provided that the derivative of what you use is equal to the original function. Okay? I'll show you the process, and then I'll try to give you a little bit of background and a little bit of why this works. So here's what you're going to do. You see a definite integral. You're going to find an antiderivative of the function. You're going to plug in the endpoints, and you're going to subtract. You got to do it in the right order, though, otherwise you get it wrong. So let's take a look, and we'll go through this, and then we'll check it on our calculator. So the fundamental theorem says if I want the area under the x squared curve from 1 to 3, I can identify that f of x is x squared. Give me an antiderivative of x squared. X to the third divided by 3 plus c. We okay with that? What rule are we using? Power rule. Okay. Now, I'm going to try to be consistent about notation, and I want you to do the same because this is how you earn marks on the exam. The integral, the definite integral from 1 to 3 of x squared dx is going to be equal to, and here's what I'm about to do. This integral symbol is an operator. And once I do the integral, once I do the antiderivative, I can't use it anymore. Because if I put it on what I'm about to write, it's going to tell me to do the integral again, right? So what I'm going to do here is I'm going to say that this integral is equal to x cubed over 3 plus c evaluated from 1 to 3. Okay, this vertical, it almost looks like half of an absolute value symbol, but this vertical symbol represents that you're going to evaluate the function here from x equals 1 to x equals 3. Okay? Another way we could write that is capital F of 3 minus capital F of 1. Now, you don't need to write both of those. I think I might, on this example, write both of them so that you're familiar with both of those notations. Okay. What that means is I'm going to put 3 in for x in the antiderivative, and then I'm going to put 1 in for x in the antiderivative. I'm going to subtract them, and that will be the actual value. So let's go ahead and do this. Capital F of 3, and important to note, this thing right here is capital F of x. Okay, so this integral evaluated is going to be 3 cubed over 3 plus c minus 1 cubed over 3 plus c. We'll take care of the c's in just a minute. If you're good with the distributive property, you already already knows what happens to the c's. Okay. What happens to the c? The c's are gone. I've got positive c and negative c, and I add them together. The c doesn't matter. The c is gone. Let's say c was 7. The 7s would subtract. They're gone. You don't need to use a particular value of c, and you don't even need to use the letter c. For the rest of the examples, I'm not even going to do it. We are going to assume, because up here it says capital F of x is any antiderivative of f of x, we are always going to use the antiderivative where c equals 0, because it's going to save us ink or graphite or whatever you're writing with. Okay? I'll demonstrate that a little bit later. So when I evaluate this, I get 3 cubed over 3, that's 27 thirds, minus 1 third. So this answer, the area under the curve, is 26 over 3. Okay? And it tells us to check with our calculator. It'll make us feel good if we can check that with our calculator. I hope we did it right. It's always touch and go on the first one here. Do you remember how to evaluate definite integrals on your calculator? Math 9. And if you have the new operating system, it looks pretty. If you have an 83, it doesn't look as pretty, but you can still do it. I'll show you the notation in a minute. I like the new operating system because you type in the bounds as you see them, 1 to 3. The function that we're integrating, keep in mind you're going to put the function as it's written in the integral. You don't want to put the antiderivative in here, because if you put the antiderivative in here, it's going to integrate again. And you're going to have a double antiderivative, which we don't, at this point, have a lot of context for. Not that we couldn't understand it, but we're not going to at this point. Okay? And we get 8 1/3. I like math frac. It always can make you double check to see that you got the right thing and we've evaluated that properly. Okay? Math frac, math, enter, enter gives you math frac. And it'll take any decimal, well, it'll take a rational decimal answer and turn it into the fraction that it's supposed to be. Okay? With the old operating system, it looks like you do math 9 again, and this notation would show up, FNINT, and it opens a parenthesis. You'd put the function in. So in this case, the function is x squared. So you're going to integrate the function x squared as means comma in the calculator, as x goes from 1 to 3. That notation would be what you use, and I hope you get the same value. Okay? So the thing with the old operating system, that's f of x, lowercase f of x. That's your variable. It's always x. If you decide to use a different variable in your calculator, you could. You could use a or m or z, whatever you want. I think it's nice to consistently use x. This is the lower bound of your integration, or I like to call that the left, because that's the left end of your interval. And this would be the upper bound. They call that the upper bound of integration. I would say that's the right bound. Okay. If you turn to the back of your notes, because there's some blank space there, and I just want to give you a little bit of the why that the f of b minus f of a works. And I want to try to connect to some of the things we've done already. So let's say, for example, and I want to connect this to velocity and time, because I think that's an easy connection for us. Let's say I have a velocity curve over time that looks like that, and I want to find the displacement between A and B. Okay? And again, like a lot of the examples last week, I'm going with a curve that's above the axis, just so you know. It works when it's below the axis too, and we'll talk about that in a minute. But what am I trying to find here? If I wanted the integral from A to B of the velocity curve, what in real world terms, what am I trying to find? Displacement. And because velocity is always positive, we could also say distance traveled. So I'm trying to find the distance traveled between A and B. Okay? Now, I'm going to make an area argument first. And because I'm finding area under a curve, is it fair to say that this integral from A to B could be written as the difference of two integrals, the integral from 0 to B of v of t, minus the integral from 0 to A of v of t. Fair argument to make? I'll shade it for you just so we have it. The integral from 0 to B is all of that in red. That's too much. It's more area than what I want, though, right? I want the blue. This first integral gives me the red. If I subtract that portion, won't I get the blue? Fair? Okay. What's the antiderivative of velocity again? Displacement. So this first integral, the antiderivative of velocity from 0 to b, doesn't that give me the displacement of the object after b seconds? Which could be found by just, what letter do we typically use for displacement? S? Couldn't we just say that's S of b? Since I started at 0, if I evaluate the displacement function after the time that is passed, doesn't that give me the displacement after b seconds? We good so far? Okay, nodding would be good at this point, or shaking your head, okay? Now, same idea here. If I start at 0 and go to A, wouldn't the displacement function evaluated at A give me the displacement of the position of the object after A seconds? It's easier if you've taken physics at this point, but can you bear with me on that? Okay, so basically what I've just reasonably concluded is that the definite integral of velocity is the displacement evaluated at B minus the displacement evaluated at A. the fundamental theorem of calculus does exactly that. A definite integral from a to b of a function is simply the area. I'm not going to do it this way. I'm going to skip that portion because that was part of the y. What I'm saying here is if f is velocity, capital F is displacement. I'm adding up the area all the way from 0 to b, and then I'm subtracting the area from 0 to a, and that's going to leave me with the area that's left. Does that make a little more sense? Okay, if it doesn't, just bear with me, and you just really need to follow the process from here on out. Okay, I like to give you a little bit of the why, though. All right, so let's do, is this the next example in your notes? We'll do this one together, and then I'll actually let you, is that the next one? Yeah, that's the next one. Let's do example 2 together, and then I'll let you go on example 3, and you'll try that on your own. Okay, so we want the area under the curve 2 sine t with respect to t, so the function is 2 sine t. dt is our is the width of a rectangle, if you will, and our bounds of integration are pi over 6 to pi over 2. So what do we need first? An antiderivative. So first of all, I'm going to write the antiderivative of 2 sine t. I'm going to write 2 cos t, except it's not 2 cotangent, 2 cos t, and how can I know for sure if that's the correct antiderivative? Take the derivative of it, because we're still, even though we've been doing antiderivatives for a couple weeks now, we're still more comfortable with derivatives. Is 2 sine t the derivative of 2 cos t? Not quite. What do I need to make it? I need to make it negative. Okay. Should I add a plus c? I could, but hopefully I demonstrated that you don't need the plus c, because they're just going to subtract out when I do the evaluating anyway, right? Okay. So this is then, I'm going to use a vertical bar to show that I'm going to evaluate that from pi over 6 to pi over 2. Okay, that's common notation for you're going to evaluate a function for 2 different t values or 2 different x values. So this ends up being, and now I like to use kind of a subtraction framework with parentheses in there, and then I do my substitution. It's really important that you get the order right, otherwise you'll get the wrong number. So which one do I do first? The upper one. So this is going to be negative 2 cos pi over 2. And this one's going to be negative 2 cos pi over 6. Cos pi over 2, 0. So this portion is negative 2 times 0. Cos pi over 6. Let's see, draw a triangle, right? Cos pi over 6. Pi over 6 is 30 degrees, right? So that's 1. Hypotenuse is double that. The other side's root 3, right? So cos is adjacent over hypotenuse, so this is root 3 over 2. So this is 0. I got a minus and a minus. There's a plus. The 2's are gone. So this is 0 plus the square root of 3. That is square root of 3. Will you check that on your calculator? Make sure your calculator is in degree mode. I'm sorry. Take that back. Calculator should be in radian mode. Will you check to make sure you get root 3 when you evaluate that integral? I'd also like you to try example 3, and I'll come around and double check to see where we're at through this one. With that second example, a couple little troubleshooting tips. My first step would be to find an antiderivative. And the antiderivative of x cubed plus 1 is x to the 4th over 4 plus 1x. And a few of you didn't include the plus 1, and we're actually going to talk about that in just a minute when I give your quizzes back too, because that plus 1 is really significant. So then we would evaluate. This would be, and I like to, again, I like to do this. I don't know if that helps you spatially or not, but I like to put the parentheses and the subtraction so I know that, so I guess I know what's coming. So this would be 3 to the 4th over 4 plus 1 times 3. This is negative 1 to the 4th over 4 plus 1 times negative 1. And I think I'm going to kind of leave the arithmetic to you at this point, but 24 is the appropriate value. Okay? If you're still working on this and you're getting 20, you're ignoring the 1, and you're really just using x to the 4th over 4 as the antiderivative, but you need the plus 1x. We'll talk about that again here in a minute. Okay? Here's the leap. You ready for the leap? This isn't crazy bad yet, right? Here's the leap. And we talked about this a little bit last week. The phrase here that's important is total area. Do you remember the difference between total area and net area? Tell a neighbor in 10 seconds what's the difference between net area and total area. Use your own words. Okay. This is one way of thinking of it. I don't know if you said it this way or not, but this is one way of thinking of it. Net area, the area below counts as negative. So above is positive, below is negative, and it cares about the sign. Total area, all area will count as positive. So let's draw a picture of y equals 1 minus x squared on the interval from 0 to 3. We know that 1 minus x squared is an upside down parabola, right? It's like negative x squared plus 1. It's an upside down parabola moved up 1 unit, and it looks like this, right? It crosses at 1, here's 2, here's 3. And when you draw that picture, I hope you see that if you're integrating from 0 to 3, you're going to have some area above and some area below. Okay? Now, if you were to do the integral from 0 to 3 of 1 minus x squared dx, what would you be getting? You would be getting net area. Because if we do the definite integral, anything that's below will count as negative, and we're going to allow it to count as negative. Okay? So, in order to get total area, without a calculator, I'm going to suggest this method. I'm going to give you a shortcut if you've got a calculator in a minute, but without a calculator, I'm going to suggest this method. Where's the break where's the break on this interval where the area goes from positive to negative? X equals 1. So the analytic way without a calculator to do this is integrate from 0 to 1 of 1 minus x squared dx. And that's going to give me the area between 0 and 1. I'm going to add to that, and I'm going to use mathematical notation for this. Some of you might actually skip the absolute value symbols and do the work properly, but I encourage you to use proper mathematical notation. The other way to write this would be plus the opposite of that, instead of using the absolute value symbols, because you know it's negative. Okay? So this would be x minus x cubed over 3, evaluated from 0 to 1. And this would be x minus x cubed over 3, evaluated from 1 to 3. That one's got absolute values, and then I add the areas together. I know that's a lot of vertical bars there, but okay. Good so far? Okay. I'm now going to go ahead and do this first portion is 1 minus 1/3 minus 0. We okay with that 0 being there? The second portion that I'm going to add, I'm going to give myself some space. I'm going to remove the picture even though the picture's good. This is going to be 3 minus 27 thirds minus 1 minus 1/3. 1 minus 1/3 in the first set of parentheses here is 2/3. I need the absolute values around the second one, guys, if I'm consistent on notation. Okay, plus the absolute value. I've got, we know what 27/3 is, don't we? Isn't that 9? So 3 minus 9 is -6, minus 1 minus 1/3 is 2/3, right? If we put that into thirds, this second portion here is the absolute value of 18/3 minus 2/3, -20/3. Okay, what does -20/3 represent now? Just pause and reflect on what -20/3 represents. It's the area beneath. The -20/3 is negative because it's below, but it's this one. If I make this drawing a little smaller, the -20/3 is this blue portion right there, right? So if I want the total area, I'm going to do 2/3 plus 20/3, and I'm going to get 20, except not 20. I'm going to get 22/3 for the total area. Okay? That's if you're not allowed a graphing calculator. Does that make sense? You have to break up and do a new integral for when your function drops below the axis. Now, the way to do that with a graphing calculator, the shortcut, is you can use Math 9, and you can do this with one integral if you use the graphing calculator. Our bounds of integration were 0 to 3, right? So 0 to 3. And then if I want to do this in one integral, I can just put absolute values around the whole function. Because what do absolute values do? Make everything positive. So if I did Math absolute value of our function was 1 minus x squared. If I do the absolute value of the function with respect to x, the calculator should give me 22/3. That's 22/3, right? Why didn't my calculator give me a fraction? It's giving me, it actually, 22/3 is 7 1/3. It's giving me an approximate because it's using an iterative process, and the absolute value function throws it off because your calculator's probably doing MRAMs. Okay? But you'll get something pretty close. Does that help a little bit? Okay? I think visually you could graph it with the absolute value of 1 minus x squared, and I think you could see it a little bit better. And the area that we're trying to find, we're going to use second calc 7. We'll start at 0. We'll go to 3. And that will give us 7.333. Okay? That's it for today. Again, like I said, we're going to do day 2 tomorrow, and then for us, Thursday is going to be a work day.